Let's talk about planets. If you don't know about ADOFAI and Ice, or ADOFAI, it's a rhythm game released in 2019 that features two planets revolving around each other and a string of tiles that match the planet's movement to the beat. The project I've been tasked with is determining the actual application of physics that takes place with the planets and determining whether or not it could be a real-life occurrence. The example we will be looking at are two planets identical to Earth, represent the fire planet and the ice planet. They will be rotating around a center with a variable BPM, also known as its period. Getting right into it, Newton's laws would be the first place to go. Starting with this first, the law of inertia. Inertia is the resistance to a change in a motion of an object. This basically means that if there is no force applied to an object, its motion will never change. Looking at our example, this means that when a BPM change occurs, there must be some external force given to both planets to alter their speed. Secondly, Newton's second law states that the net force on an object is equal to the mass times the acceleration of that object. If we view the gravitational force as a centripetal force which acts like a normal force, the tangential force can be calculated. Again, assuming that both planets have the same mass and radius as of Earth for simplicity, this brings the equation to F is equal to 5.97 times 10 to the 24th times the BPM divided by 60 times pi, where its acceleration is equal to the beats per second times pi, which is equal to radians per second. Plugging in 100 BPM to this results in a tangential force of 26.15 times 10 to the 24th power newtons, which already seems extreme, especially when inputted with larger BPM values. Newton's third law states that for every action there's an equal and opposite reaction. An example of this is the gravitational force applied to both planets. When one planet increases mass or changes distance, both planets experience the same change in gravitational pull. Static and kinetic friction are not applied in this example. Static friction occurs when an object is at rest, while kinetic friction requires another surface to occur. Even if we view air resistance as a frictional force, both planets move with perfect speed with no dampening, which shows that there is no air in this example. If we assume that both objects are of the same mass, the center of mass should always be the middle of both objects. Because both planets move around a center point, this center point will always be the center of mass. The formula to calculate this is position 1 times mass 1 plus position 2 times mass 2, all over mass 1 plus mass 2. To calculate the gravitational force, we need to use the formula Fg is equal to g times mass 1 times mass 2 over distance squared. If we assume that in this example that the distance between both planets is their own radius times 6, we can calculate r to be 38,268.6 kilometers. Earth's mass is equal to about 5.97 times 10 to the 24th power, or 6 septillion kilograms. The constant, g, is the value of the natural force applied to every and all objects in the universe, which is equal to about 6.67 times 10 to the negative 11th power. Plugging all numbers into this equation, we get 1.62 times 10 to the 30th power newtons. The problem is that these planets are always a constant distance from each other, no matter the tangential speed. This whole time, we have treated the gravitational as a centripetal force because both planets are physically bound to a certain radius around the center of mass. This means that whenever a BPM change occurs, both masses must alter their own mass in order to maintain equilibrium. This may have been obvious from the start, but these parameters have no real-life examples. Altering mass and creating energy from a BPM change is impossible under any circumstance. While it may be a little disappointing, a dance of fire and ice is unrealistic in terms of physics applications.